Vous êtes sur PIMS.
Bienvenue sur PIMS,
Le séminaire de philosophie des invariants mathématiques.
Okay, thank you very much. So, hello everyone. So first of all, I have to speak in English because my French is not good enough for a research talk. First of all, I would like to thank Frederick for this really wonderful invitation and for inviting me to this seminar on the philosophy of invariance. We talked a bit just before the talk, on the importance of this notion of invariance, not just in logic and mathematics, but really in the history of 20th century philosophy. And I think it's really a crucial notion. And I think this is a very interesting research seminar that Frederick is organizing here. So the idea for my talk is, or the topic of my talk is philosophy of mathematics, as Frederick mentioned. And specifically, what I want to discuss today is a particular understanding of structuralism in the philosophy of mathematics, or a particular account of structuralism in philosophy of mathematics. So the main question motivating this talk is, well, how to cash out this notion of implicit structure of mathematical objects. And as I said, structuralism is really the background idea, or the main philosophical background for this talk. I mean, I'm sure most of you know this, but structuralism as a philosophical position is usually characterized as the view that mathematics is the science of abstract structures, right? And one way to understand this is to say that mathematical theories describe the structure or the implicit structure of objects such as number systems, graph, geometric spaces, and so on. What I want to do today is offer you two possible ways to understand this notion of implicit structure. So two ways to characterize the notion. And the two approaches are the following. So one is a language-based approach based on the notion of definability of some form. And the second one, connects my topic to the research seminar here, is an invariance theoretic approach. So based on the notion of symmetry groups, automorphism groups, or isomorphism groups. And basically what I would like to do is present these two ways to characterize implicit structure, and then say some things on how these two ways of thinking about structure can be related or put into relation with each other. So here's an outline of my talk. I will first say a little bit about structuralism in general, and then more specifically about the history of structuralism. So I have some slides on Hermann Weil's early work on philosophy of mathematics. And what's interesting about this book Weil's book that I'm referring to, is that already there, so that's 1928, I think you can see two ways to think about structures, mathematical structure. Okay, so this first part will be a bit historical. Then I would like to give you a case study to further flesh out these two ways of thinking about structure. And the case study comes from finite geometry. And then the third part of the talk will be really where I make my main claims. So this is the section on the two ways of characterizing implicit structure. And then in the fourth part, I will offer you a formal framework using the notion of Galois correspondence to specify the relation between these two ways of thinking about structures. So in particular, this section will be on what's usually characterized as a certain duality between these two approaches, so the invariance approach and the definability approach. And then finally, I'm not sure if there will be enough time, but if there's enough time, I would like to make a couple of remarks on the notion of structural equivalence or sameness of structure. So the question when two, or under which conditions, two mathematical structures are similar or equivalent with respect to their implicit structure, right? So that's the idea. Okay, so that's the outline. So let me start. So two ways to think about structure. As I said, structuralism is the background here. In fact, I should say that I don't have a particular view or philosophical theory of structuralism in mind here when I talk about implicit structure. What I give you here is a kind of deflationist account of what a structuralism could be. I mean, I'm sure you know that there are these different philosophical theories of structuralism, some more realist, Shapiro's anti-Rehm structuralism, I'm sure you've heard of this. Then there are more nominalist or eliminalist theories of structuralism, Hellman's modal structuralism. Here in this talk, I will assume a very minimal account or deflationist account of what structuralism is. And basically, this is my kind of working definition for today. I take structuralism to be the view that mathematical theories study only or maybe primarily the structure or the structural features of their objects. So features not concerning the internal or the intrinsic nature of objects such as numbers, but rather their relational properties. So properties concerning how these objects relate to each other within a given system, right? So think of the theories of the natural numbers, so Peano arithmetic. The idea would be that PA does not describe numbers as specific sets, for instance. That would be a kind of reductionism, set theoretic reductionism. But really, the business or the task of the mathematician is to show or investigate properties concerning how numbers add up, how they can be divided, and so on. So it's focused on the relational features of these objects. So here are two, I think, very nice quotes, passages from the philosophical literature where this thesis of structuralism is characterized or is summed up. So the first one is from a more or less recent paper by Øystein Linebo, one of the central figures in this debate, and Linebo says, very roughly, mathematical structuralism is the view that pure mathematics is the investigation of abstract structures, and that all that matters to mathematics is purely structural properties of objects, right? So it's about the structural properties or the structural relations, not the intrinsic features of these objects or intrinsic characteristics. And then there's a second quote, I think along similar lines, that's from an older paper by Jeffrey Hellman, who says that on a structuralist view, the mathematician, I think there's a typo, the mathematician claims knowledge of structural relationships on the basis of proofs from assumptions that are frequently taken as stipulative of the sort of structures one means to be investigating. So, paraphrasing Hellman, structuralism is the view that mathematics concerns only structural relationships about objects that have been specified axiomatically. I think that's the idea. So assumptions taken as stipulative of the sort of structure. So I think the idea alluding to here is just that you introduce by axiomatic stipulation or by axiomatic definition some type of structure, natural number structures, and then you focus on, you investigate the structural relationships between the objects in such systems. Also, another quote closely related to this structuralist view is that this focus on structural features or structural properties really gives you an important condition or criterion for identity between mathematical objects. So the idea really is that two objects are identical or equivalent if they are structurally similar or if they are isomorphic. And in fact, in a recent paper by Steve Audi on this, Steve Audi calls this a principle of structuralism, right? Isomorphic objects are identical. So that's the structuralist identity or structuralist equivalence criterion. And we'll come back to this issue, what a proper or adequate identity criterion for structures should be. But the idea expressed by Audi is this, right? So you have two objects, so here two graphs, two Peterson graphs. These are clearly distinct objects, right? But from a graph theoretical point of view, these two are identical, right? Because they are isomorphic, right? They share the same structural features. So that's the idea. Okay, so here, this was a very quick introduction to some ideas in structuralism. Let's look a bit at the history or the prehistory of this view, right? As you might know, structuralism in the modern philosophy of mathematics, analytic philosophy of mathematics, has often been identified with this famous classic paper by Paul Benasarev, 1965 paper, What Numbers Could Not Be. Very nice paper. If you haven't read it, have a look. It's really a classic paper. But in fact, I think one can or should say that this identification is a bit misleading, because there has been, obviously, I would say, a rich mathematical history and prehistory of structuralism, both within mathematics itself. So in particular, there have been different methodological developments starting in the 19th century within mathematics that in some way led to a structural turn in the field, right? So just to give you some examples, or what's usually mentioned here, the development of modern axiomatics, the development of abstract algebra, so of group theory, for instance, and the use of group theoretic methods in different fields. Take for instance, Klein's Erlangen program in geometry. Foundational debates in the 19th century, in particular the development of set theory and then category theory a bit later. So I think these are all developments in the 19th and early 20th century that clearly brought with them kind of a structural conception of mathematics. And also one should say that from quite early on, so I would say at least beginning of the 20th century, there have been, you can identify structuralist accounts or philosophies of mathematics in different philosophers and different thinkers. So just to mention a couple of names here, Ernst Cassirer, we just talked about or mentioned his name, I think it's clear that he should be characterized as an early structuralist. So in particular, if you look at his famous early book, 1910 book, Substance Concepts and Function Concepts, I think is the English translation, Substanzbegriffe and Funktionsbegriffe. I would say that's a structuralist manifesto. So he definitely gives a structuralist account of modern mathematics in that book. Another figure to be mentioned here, I think, is Rudolf Carnap. Starting in the 1920s, Carnap's work on the philosophy of mathematics was clearly structuralist in the modern sense of the term. Another figure one could mention is, I think, Husserl's early work. Mirja Hatimo, for instance, has worked extensively on Husserl structuralism. And one other early philosopher, mathematician that I think should be mentioned here is Hermann Weyl, even though, as you might know, Weyl has had different views, especially in the foundational debate. So he was an intuitionist for a while. He extensively worked with and on Hilbert's program. But I think there is, in Weyl's early work, there are some structuralist ideas that are worth cashing out. So this is what I want to tell you about now. So I should say I'm absolutely no Weyl expert. So I basically look at this book, early book by Weyl, Philosophy of Mathematics and the Natural Sciences. And I think one could argue that here in that book, Weyl presents some structuralist ideas. In particular, in his discussion of geometry, one can find a distinction between two methods or two ways to characterize the structural or objective content of theories, namely the axiomatic approach on the one side and a symmetry or invariance theoretic approach on the other side. So let me give you some quotes to illustrate this. So here's what Weyl has to say on axiomatics. And when he talks about the axiomatics, he has a section where he discusses Euclid, but really the focus is modern axiomatics, so Hilbert. So here's Weyl. That's an early book. That's an old picture of Weyl, but I didn't find a better one. So here's the old Weyl. Doesn't really match with the early text, but so here's what he says on axiomatics. The method consists simply in making a complete collection of the basic concepts, as well as the basic facts from which all concepts and theorems of a science can be derived by definition and deduction respectively. So you have an axiomatic specification of basic concepts, an implicit definition. I think he uses the term at some point. And then you can get information by deriving theorems, and this is done by deduction and by definition. So the notion of definition is used explicitly here. And as I said, the background or his model for modern axiomatics is clearly Hilbert. So he talks about Hilbert's Foundations of Geometry, so this famous 1899 book. And Weyl discusses Hilbert's book as giving an axiomatic description of what he calls the structure of space. And it's interesting to note that Weyl uses the term structure here in the late 20s, right? Struktur des Raums, that's the term that he uses. And really, to a modern ear or modern reader, this is his presentation of modern axiomatics and axiomatic theories is quite modern and structuralist, one could argue. So he says, for instance, that an axiom system presents a logical schema of possible sciences. So the idea defended by Weil is that an axiom system does not describe a single system, but really it defines a higher level entity, a structure that is then or can be instantiated by different models or by different systems satisfying the axioms, right? So Weil already in 27 or 28 makes this distinction between systems and the structure that is shared by isomorphic systems. So one could argue, I'm not going to go into that, but one could argue that here you have the roots of the terms of a model theoretic conception or proto-model theoretic conception of theories. The interesting question, also historically speaking, is how does he understand this notion of structure in 28? And interestingly, or unfortunately, he doesn't really specify it. He's a bit elusive on the topic, but he makes some really interesting remarks on the relation between systems and structures. So systems or models, he calls them also domains in the English translation. Here's what he says, for instance. Isomorphic domains may be said to possess the same structure. So isomorphic systems or models have the same structure. And then I won't read this, but then he goes on to say that something like an isomorphism lemma holds. So whenever you have two isomorphic systems, then they satisfy exactly the same sentences. Hey, Julian, sorry, I didn't see you before. Nice to see you. And secondly, and that's really structuralist in spirit, he says, a science can only determine its domain of investigation up to an isomorphic mapping. In particular, it remains quite indifferent as to the essence of its objects. That sounds like Shapiro, or one could argue. Okay, so this is Weil on the axiomatic method, clearly spelled out in I would say in a structuralist language. But then he says in the later parts of the book, he says that at least in geometry there is a different way of cashing out or characterizing structure, a non-axiomatic approach, and that is based on the study of geometrical space in terms of the notion of invariance under transformations or invariance under symmetries. And the background here is, of course, not Hilbert's Grundlagen, but Felix Klein's famous Erlangen program, as outlined in this programmatic paper of 1872, comparative investigations. I forgot the last part of that. I'm sure. It's the famous 1872 paper. And the basic method here, so Weil refers to Klein, and the basic method that he discusses here is the following. So one considers a group of transformations acting on a given space, and the objective properties and relations of figures in that space or configurations are specified as those invariant under these transformations. So the idea is, Weil's idea is to identify the objective relations with those relations preserved under the transformations, or those relations invariant with respect to the transformations in question. So here's the idea. So this is an interesting passage from Weil, because here I think that you can find two philosophically interesting ideas related to this Klein's approach here. The first one is that the focus on transformation groups gives you a notion of what he calls likeliness or similarity, and now one could say structural similarity. And the second idea is it gives you a notion of when a relation or property is objective. So it gives you a notion of structural property, one could say. So here's Weil discussing Klein, basically. So we start with a group of transformations. It describes, as it were, to what degree our point field is homogeneous. Once the group is given, we know what likeliness or similarity means. Namely, two figures are similar that arise from each other by a transformation of this group. That's the first idea. And second, also under what condition a relation is objective. Namely, if it's invariant with respect to all transformations. So here you have the two philosophically interesting ideas related to the invariance approach, Klein's invariance approach. It gives you an idea, so translated into modern structuralist terminology, it gives you an account of structural equivalence of figures in a space or configurations, and it gives you a notion of structure, what the structural properties are. Okay, so much for the history. Yeah, this was a couple of remarks on Weil. But I think it makes sense to illustrate this a bit further, or discuss these two approaches by looking at a specific case study or a set of examples. And the examples that I bring are from finite geometry. It's a really interesting field of geometry that has one big advantage. As we talked, it's fairly simple, or you can understand or grasp what the relevant structures are here. But at the same time, you have these two approaches to further elaborating what the structural features are. So, okay, let me just walk you through this. So the objects or the structures that we study here are these called incident structures, and these are, set theoretically speaking, very, very simple mathematical objects. So they're basically triples consisting of a set of points, a set of lines, and an incidence relation, a binary incidence relation that can be that represents the incidence relation between points and lines. So a point lying on a line, or reversely a line going through a point. And our focus here will be on two specific types of these finite incidence structures, namely affine and projective planes. Okay, so I won't have anything to say here about spaces, but it's really, let's start from the most simple structures that we can look at. This should be said here, there are two ways of specifying, of constructing such planes. There is the algebraic construction in terms of vector spaces over finite fields, and in the literature, the study of affine and projective planes is usually called Galois geometries. I won't have anything to say on this today, but I will focus on the second approach, the axiomatic characterization. So what Weil also discussed in his book. So here's an axiomatic theory of affine planes. That's fairly simple. So the idea is this: an affine plane is just an incident structure. So this a triple of the form just specified that satisfies or that has the following three properties, or satisfies the following three axioms. So any 2 points are incident with a unique line. That's the first axiom. Then there's something like parallelity. Given any line and any point P not lying on the line, there exists a unique line M such that P lies on M and L and M do not intersect, right? So given a line and a point, there exists a parallel line running through P and parallel to L. And then the third condition to be met is there are at least 3 points in such an affine plane that are not collinear, that do not lie on the same line. So here's a really beautiful, simple affine plane, so an incident structure which satisfies these criteria. That's an affine plane of order 3. And just given the way we have introduced or specified these planes, there are a number of kind of basic structural facts to say or to prove about these objects. So just to give you some examples, so for every affine plane of a given order, and that means the number of points on any given line, one can say that every line is incident with exactly q many distinct points. Every point is incident with exactly q plus 1 many distinct lines. There are q square many points in the affine plane of order q and so on. Okay, so these are basic facts that you can prove about these objects. So this was affine plane. So quickly on projective planes, these are also incident structures that have other properties. So and the 3 axioms are following: every 2 points are incident with a unique line. Then there's a dual axiom: every 2 lines are incident with a unique point. And then 3, there exist at least 4 points, 3 of which are not collinear, not lying on the same line. And a simple structure, a simple object that satisfies these conditions is the so-called Fano plane. Okay, so a different structure, axiomatically specified a different structure, different incident structure than an affine plane. Okay, so so it's interesting that the reason why I chose these examples is, I mean, as we talked about before, these are fairly intuitive, simple structures, right? But nevertheless, there is a lot of very rich and technical literature on these objects, right? Investigating these objects. And I think what is done in my very limited understanding of finite geometry is that these structures are studied both synthetically and analytically in terms of Galois fields, in the sense that one investigates the internal structure, the internal composition, the structural composition of these planes. And this investigation of the internal or inner structure is usually related to the study of so-called configurations, so definable point sets, for instance, in these objects. Many theorems that you find in the textbooks, I think I should refer to the Dembowski 68 book. I think that's a classic book on finite geometry. These central theorems state combinatorial facts about such configurations. And by configuration, so point sets, I mean objects like these ones. So arcs, for instance, okay? An arc is a set of points, a subset of points in such an incident structure. So a set of k points. k larger than 3, such that no 3 points of A are collinear, right? That's a simple object. An oval in a projective plane would be a similarly simple type of configuration, okay? So it doesn't, the details really don't matter. I just want to point to you that these are the objects, the internal objects, or the internal objects investigated in the research. And how are they investigated? One focus here is on the study of the structure-preserving mappings or automorphisms of such objects. The automorphisms of such incident structures are usually called collineations, and the collineation of such an incident structure, again understood as a triple, right, set of points, set of lines, and a binary relation, is an automorphism. So it's a pair of bijections that preserve the structure, the incident structure, right? And as we know, the class of all collineations of a given plane, so think of the Fano projective plane, that forms a group, right? So we have a group structure here. And to come back to Weil, one can say in Weil's terminology that different relations are objective or structural in the sense that they are invariant relative to these groups. So the most simple examples are collinearity and parallelity of lines. Collinearity of points is preserved under the group of all collineations of the, so all automorphisms of the Fano plane, okay? Collinearity and parallelity of lines is preserved under the automorphisms of the affine plane of order 3 that I mentioned, okay? And more generally, I won't go into this here, but the important point I want to emphasize here is that this use or focus on automorphism groups or subgroups of the automorphism of a particular structure, that's usually or related to the study of the internal structural composition, okay? So here, just to give you one quote from one of the textbooks on this. So this is Tsutsuko on finite geometries and finite groups. He says the automorphism group of a design, and by design he means such an incident structure, is closely related with the structures of that design. And as you see from here, I mean, what he means by structure, it's not the object itself, that's the design, it's the structure of the design. So it's the internal or implicit structure, if you will. So, I mean, I've said this before, there's a close connection between the structural composition of these planes and subgroups of its automorphism group. And one, I think, typical question in the study of these configurations, like arcs and ovals and others, is, for instance, this one, a typical question. For some configuration of a given plane, determine the subgroup of its automorphism group that leaves the configuration invariant. Okay, so I think that quote really nicely sums up the point I want to make here. Okay, so we see now, or I hope to have shown that mathematics, at least in this particular case study, can be understood as the study of the internal structural composition or the implicit structure of a mathematical object. So how to make that precise. I think one point, so I tried to be, this is in some sense really, I want to make a really basic point here. But I think what one saw, or what one can see from the case study already, is that there clearly is a distinction between some form of primitive structure. So the objects themselves that are investigated and their internal or implicit structure. So I think that distinction needs to be made, and usually the implicit structure is specified axiomatically. So what is the implicit structure? Well, in the example that we just saw, it was a relational system, right? So and generally one could say it's a relational system that is a tuple with one or several domains of objects and then a bunch of relations on the domain or relations connecting the domains. And more generally, one could say it's a structure consisting of one or several domains, a bunch of relations, possibly a bunch of distinguished elements. So think of the zero in a natural number system, and a bunch of functions or relations, right? So these are the primitive structure, I would say. And in this very nice paper by Saunders McLean from 1996, I think the paper is called Structure in Mathematics. It's a really nice paper. He characterizes the notion of structure in precisely this sense. So McLean says, a structure is essentially a list of mathematical operations and relations and their required properties, commonly given as axioms. Okay? So we just take for granted here that primitive structure is specified axiomatically. I mean, that's not a big point. So let's assume that the question is then how to think of the implicit structure of such a primitive structure, such a system. As I said, mathematics can be understood as the study of the implicit structures of such systems. And one could kind of paraphrase that claim as saying that the implicit structure of a system is determined by the structural properties of objects in the domain, namely properties that respect this primitive structure. So mathematics can be understood as the study of structural properties, properties that respect this primitive structure. And now there are two ways to cash out the notion of structural relations or structural properties in mathematics. As I said in the beginning, one is a language-based approach and one is an invariance-based approach. So let me make a suggestion how to think about structural properties or relations along these lines. So first, implicit structure via symmetries or invariances. And here we can, in fact, come back to Weil and a very, I think, a well-known passage from this little book, a popular book on symmetries that Weil has written. So here he says, whenever you have to do with a structure endowed entity, so an object with some internal structure, try to determine its group of automorphisms. You can expect to gain deep sight into the constitution of that object in this way. So looking at the group of automorphisms will help you get insight into the constitution of structure of this object. And this Weil's idea has been taken up in a paper little-known paper by Winnie from the mid-80s. And I think it's worth looking at Winnie's characterization of Weil's approach. So Winnie in this paper says this: Weil's basic idea is this: a change that makes no difference in a system K can make no difference in the structure implicit in K. So note that Vinny actually uses this notion of implicit structure here. This gives us the following criterion of implicit structure. So S is implicit in a system K, just in case if S is preserved by every change in the system that makes no difference, that is, S is preserved by every automorphism of K. In that case, we shall say that the property S is an invariant of the system K. Right? So Winnie identifies here the implicit structure or properties that he takes to be implicit structure about a system with the invariance. So there's an easy way to make this a bit more precise, right? So one could say that the property of object, understood extensionally as a set of objects of A, is a structural property if it's invariant in A. That is, for every element in the automorphism class F, the property is preserved by F. So Fp equals P, right? I think that's the most kind of straightforward explication of what a structural property is, following the idea of Weil and then Winnie. Excuse me. But as we saw, so this is a specification of structural properties in terms of invariance relative to a given system, right? So it's a local specification in a sense, right? It looks at a particular system and it specifies invariance in terms of the automorphisms of that system, right? But we saw already in Weil, so in 28, that Weil is not kind of restricting his focus to particular systems, especially when he's talking about axiomatics, but he's looking at different models and isomorphic models, right? So what we should do, given a modern model theoretic account of theories, is to give a definition of structural properties in terms of invariance, but give it in terms of invariance across models of a theory, right? Not looking at a particular system, but looking at invariance across models. But doing this presupposes, in a way, to specify what we mean that a particular mathematical property applies to different models, right? So take a simple example, some number theoretic property of being an odd number, of being a prime number. How is that applicable to different models of our theory of second order Peano arithmetic, for instance, okay? So how to think about mathematical properties is really the question here. Or,
can I just ask one question?
Sure,
so
sure.
By model, you mean instantiation?
Yeah. Yes, I would. So I'm kind of what I do here now is I'm shifting the. So I'm just assuming a modern model theoretic understanding of theories now. So I assume that we have an axiomatic theory, second order Peano arithmetic. That's the typical. That's the example that philosophers like to use a lot. So we have a theory. That theory specifies a class of models, namely natural number structures. And now the question is how to specify properties of objects in such models, right? So models in the sense of instantiations of a general structure, but I'm assuming the model theoretic framework here. Or think of the property of being a maximal arc in different affine planes, to stick to our earlier example. So how to think of mathematical properties here? Well, one possible way to go here, and this has been, so I've worked on this a bit with a colleague, Johannes Korbmacher, and we've published a paper on these different ways of thinking about structural properties. So if you're interested, I'd be happy to send you that paper. In that 2018 paper, we make the following suggestion to think about properties of mathematical objects more intentionally in a way. So here's our suggestion. So let P be a property of objects or elements in systems of a given mathematical type. So for instance, systems or models of second order Peano arithmetic, okay? Then it makes sense to distinguish between a local extension of such a property in a particular system, so in a particular natural number system, basically as the set of objects having that property in that particular system. So taking our example of being a prime number, so the set of primes in a particular natural number system. And then one can specify the property P generally or intentionally as a function that assigns to every such T system, so every natural number system that maps to every natural number system this local extension of P, okay? So to stick to our example, the property of being prime is the function that for every natural number system gives you the class of prime numbers in that system, gives you the local extension, okay? So we have a bit more a general definition of what mathematical properties are that you need if you want to define structurality or structural properties in terms of invariance across models. So now the question is, well, what's this more global notion of structural properties, how to specify that? And the idea is this. So let S be a system of a specific type, axiomatically specified type. Then P is a structural property of the objects in the domain of such a system S. If for all other systems, T systems, S prime, and for all isomorphisms, okay, I kind of lost track here. Okay, let me go again. So we say P is a structural properties of the object in the domain of one particular T system, if and only if for all other T systems S prime and for all isomorphisms delta, if an object belongs to the local extension of P relative to system S, then the isomorphic copy of that object belongs to the local extension of P in the system S prime, okay? So basically the isomorphism preserves the extension of these properties. So if X is in the local extension PS, then delta X, so the image of X given by that isomorphism is in the local extension of P relative to S prime. Okay, so this was my proposal for thinking about implicit structure or structural properties along the invariance theoretic line. Okay, but as I said before, there is a second alternative way of thinking about implicit structure, and that is language-based, that is based on the notion of definability. And here we can again draw two different sources for this. One is again Winnie's paper. And Winnie's idea is of characterizing implicit structure via definability is the following. So this is from the same paper, and I should say something on the context here. So in this passage, Winnie discusses systems, natural number systems, and I think the primitive structure is a tuple consisting of n, so a set of natural numbers and an ordering relation. So that's the primitive structure in this particular case. And then he is discussing whether it's okay to include a successor function or a symbol in the language standing for a successor function. So S here is not primitive, but it's added, okay? And here's what he says. So if we are content to supplement this primitive structure by S, we regard the definability of S as a sign of its implicitly being in the structure N. Okay, and recall N is the structure consisting of a set of natural numbers and a strict ordering. Definition in this case anyway is used in the sense of singling out an entity implicitly present for explicit consideration. That's really crucial, I think. So Winnie's distinction between implicit structure and how to make it explicit and definability is one way to go here, according to Winnie. And then a bit more recent, a nice passage from Wilfried Hodges. I think that's from the Shorter Model Theory textbook, where Hodges says, structure is whatever is definable. A merit of this slogan is that it gives us a means of controlling the host of implicit features of a structure A. So here again, you have this notion of implicit structure or intrinsic structure, okay? So how to cache that out? Well, what you need for this is obviously a notion of definability. And I think since we talked about Hodges, and Hodges model theory, I think a natural candidate here is the model theoretic notion of definable relations in a structure. So here's definability again as a structure local concept. I will spare you the details here, but this is the textbook definition of a definable relation or property of objects in a given L system M. So if you basically it says that it's definable if there is a formula in the language that specifies the extension of that property. And then given that definition, you can again specify what structural properties are. And you can do it again locally, as I've done with the invariance approach, but you can also do it globally. So I'll spare you the local definition, but move to the global one right away. So we can say that a property P is a structural property of elements in systems of a given type T. If there is a formula in the language of LT, such that for every system S of type T, the formula specifies the local extension of P in every system of that type, right? So it's a structural property if it's definable, if the local extension is definable in every T system. notice that, I mean, these two accounts of thinking about implicit structure or structural properties, implicit features, they are, from a conceptual point of view, they are really distinct, right? So they're two very different ways of thinking about implicit structure, right? One is, in a way, object-based. So you look at the class of objects and then you specify structurality in terms of invariance conditions. So you specify structurality in terms of what is preserved under some transformations, right? It's language independent in a way. And the other approach is based on the linguistic representation of these structures, right? So you say there a property or relation, so some information, implicit information, is structural if it's definable in the language. So if there's a formula in the language describing that structure that carves out the local extension of that property, right? Or defines that property. So given that, an obviously interesting question is how are these two ways of cashing out implicit structure of a mathematical object related, right? So think again of our case study, affine planes. The parallelity relation is both definable in the language of incident structure. I didn't give you the definition, but it's very easy, straightforward. And it's, as I mentioned, it's also invariant under the collineations or the automorphisms of an affine plane. But what is the general relation between these two approaches? And interestingly, this is a question that was already raised or discussed by Weil in the 20s. So here, recall that Weil's context, so the context here is geometry for Weil. And Weil makes the following very interesting kind of remark on the relation between the two. He says that a point relation, so a relation between points, is said to be objective if it's invariant with respect to every automorphism. In this sense, the basic relations are objective, and so is any relation logically defined in terms of them. Okay? So every primitive relation, every axiomatically defined relation, plus every relation definable in that language turns out to be objective according to the invariance approach. So definability implies invariance, one could say, okay? What about the other direction, right? That's the interesting question. And here, Weil doesn't say a lot, right? So it's basically one sentence. So he says, whether every objective relation may also be defined raises a question of logical completeness. And he doesn't go much further what he means by that 2028, right? So this is before the important methodological results were introduced by Gödel and Tarski and others. So for him, this was kind of an open question, right? But interestingly, more can be said about this. And Frederic, now I should ask you how much time do I still have, or should I use?
How much do you want?
Okay. Is it okay if I go on for 10 more minutes or so?
It's okay, yes.
Yeah,
Okay,
perfect.
Thank you.
I hope it's okay for. So then I would have two more sections, but in the interest of time, let me say something on this relation between the invariance and the definability-based approach. So more can be said than what Weil did in the 20s. And let me start by saying that many logicians and mathematicians have noted that there is a very interesting duality between these two ways of thinking about structure, right? So here's a nice passage in Hodge's model theory book that really I think it's a really nice passage because it points exactly to this duality. So here he says, in a sense, structure is whatever is preserved by automorphisms. One consequence of this is that a model theoretic structure implicitly carries with it all the features which are set theoretically definable in terms of it, since these features are preserved under the isomorphisms. There's a rival model theoretic slogan, and I've given you that passage: structure is whatever is definable. Surprisingly, this slogan points in the same direction as the previous one. So, I mean, as Hodges points out, obviously there's from a model theoretic point of view, there's an interesting connection between these two approaches.
Can I ask you one clarification question?
Sure.
So, I'm just looking, this whatever is, there's some sense of what this whatever is. Are we talking about relationships? In other words, structure is whatever is preserved by isomorphism. But if the rival theoretical model is structure is whatever is definable, whatever is also is the relationships among objects, and it's not surprising to me that those two be crude. I mean, for example, take a successive function. It's specifying not the object itself, but a relationship between objects.
Yes,
right?
yeah.
Similarly, isomorphisms are preserving relationships between objects.
Yes.
So given that's the case, it doesn't seem to be surprising that you would.
Yes, so I will try to make a bit more explicit how I view this. But one thing I could say right away is that it is the question always concerns relations or properties. So, but let's talk about relations between objects of a given system.
So whatever is therefore in a rival theoretical model is not.
So whatever I think I would. That's how I would read it, right? So, or at least for the sake of the argument here, let's restrict it to relations. Okay, could be of any arity. Okay, but let's focus on relations. So let's not talk about operations or functions. Let's keep it simple here. And then the question is, well, what is the relation between the invariance theoretic approach of characterizing structural relations to the definability-based approach? That's the idea. But the things investigated here are relations between objects of a given system. Okay. And I think what Hodges is drawing to here, and what has been discussed also in work by Bonnet and Engström and by many others, in fact, is that there is a dual character of invariance under transformations and this notion of definability in some formal language or definability by some logical operations. And interestingly, I think this holds also for the two ways to think about implicit structure. So for instance, this Bonnet, so this is Hodges is on general model theory, right? The Bonnet-Engström papers are on logical constants. So they discuss this duality in the context of logic, philosophy of logic. But I think one can also apply this idea to our context of implicit structure and structuralism, so philosophy of mathematics. And in fact, what I propose in this paper is that one can give a formal explication or an explication of this duality in terms of a Galois, so-called Galois correspondence between automorphism classes and sets of relations. So in the last 10 minutes or so, let me let me outline what I have in mind here. So again, the idea is really to make precise how these two ways of thinking about structure are connected or can be connected. And in order to do so, I have to give you some. This is very basic, but some terminology to start with. So now we are here again in the local approach. So we look at sets of objects, right? So we don't look at models of theories, but we look at particular sets of objects and relations on them. So let D be a non-empty set. Then we can specify the class of all permutations of D, call that sim D. And then we can specify the class of all relations on D of a finite arity, okay? And for a given relation of n-ary relation, we can say what induced relation by permutation is. So for a given R, a permutation, so an element in this class sim D, we can say that the relation induced by G is just this thing here, right? And then finally, we can say when a relation on D is invariant under a given permutation G. And I mean, that's basically what I told you before. So G is, or R is invariant by G, or R is preserved by G, or G preserves R, if and only if these two things are equal, extensionally speaking, okay? And given this very simple setup, we can specify two interesting operations, right? So consider now a set of relations on D, so bold R, a subset of the set of all relations, and consider a subset of the permutations of D. Then one can define two operations, namely out R and inf G, and these are informally speaking the set of, so inf G gives us the set of relations invariant relative to this subset of permutations. So it gives you a set of relations. Starting from a set of permutations, it gives you a set of relations that are invariant. And this gives you the set of automorphisms, right? So starting from a subset of relations on a given domain D, out R gives you the set of permutations that are automorphisms. And these two operations form a Galois connection between sets of relations on D and sets of permutations. And I won't give you the definition, but what you have is that these three conditions, these three stating relations between subsets R1, R2, and G1, G2 hold. So there's a Galois connection here. The interesting point for us today is that this gives us a very simple set theoretic framework, gives us a nice background for specifying these notions of implicit structure again, right? Given some relational system with, say, one domain of objects and a bunch of primitive relations, what is the implicit structure? And what I just mentioned here, you can take this set, this set here, so that the class of invariants under the automorphisms of R as representing the implicit structure of that model. So that's the invariance-based account. And that's the first account. And secondly, you can also characterize the implicit structure of a given model in terms of the class of all definable relations in M. So let's call it def M, okay? This is just the class of relations that are definable in some formal language. So in some L definable for some formal language of which M is a suitable structure. And then we can specify the two ways of thinking about implicit structure in terms of closure conditions. And two important notions from Krasner algebra, or yeah, I think the field is called Krasner algebra, are relevant here. The first one is the notion of a Galois correspondence, a Galois closure. And this is a fairly simple idea. The idea is that a set of relations, so a subset of this class of all relations, is Galois closed if it is closed under this operation inf out. So if R equals the class of all invariants under the automorphisms of R. Right? So that gives us the invariance theoretic approach. And concerning the definability theoretic approach, there is a similar notion. There's a so-called Krasner algebra. And what this is it's defined as follows. So given a class of a set of relations, we say that this thing here is the Krasner algebra generated by R if it's the least or the smallest set of relations on D that contains R and that is closed under logical operations. And I mean, in our context, closed under definability in the first order language, okay? And given these two notions, we can then specify what the relation between the two ways of thinking about implicit structure actually are, how they are related. Here's the general result. I don't know when this was proved first. I refer here to a paper by Schieler and Börner from 2003, but might have been, it might go back to Krasner, I guess, I'm not sure. But the idea is this: so for any subset of relations of the class of relations on D, if I is Galois closed, then it's a Krasner algebra and an intersection closed Krasner algebra, which basically translated into our framework means that every piece of implicit structure, if it's definable, then it's invariant, right? So definability implies invariance. So the definability account of implicit structure is the more fine-grained account, so to speak. The question is, what about the reverse direction? And here the general result clearly does not hold, but there are some very nice special cases, extra conditions, where the two approaches to implicit structure actually turn out to be equivalent. So the general equivalence that doesn't hold, but in these two limit cases, I'll just give you the theorems, but in these two limit cases, you actually get the equivalence between the definability approach and the invariance theoretic approach. So on the lower bound, on the one side of the spectrum, you have the finite or the denouemably infinite case, and here you have the theorem that for any set of relations R on a domain D, if D is countable or finite, then R is a Galois closed if it's an intersection closed Krasner algebra, and vice versa. So you get the link, the equivalence here. And on the other end of the spectrum, you get an equivalence if you tweak the notion of definability to the limit case where you allow definability in an infinitary language, right? So for any R is Galois closed if and only if it's closed under definability in an infinitary language. So a language allowing infinitely long chains of conjunctions and disjunctions and quantifiers. So these are the two limit cases. And again, to kind of to wrap up, what this framework of Krasner algebra gives us is a kind of a formal framework for specifying the relation between these two ways of thinking about implicit structure. And they show that invariance is a much more comprehensive approach. Definability is much more fine-grained in a way. So they are not equivalent, these two approaches. But what these results show us that in certain cases, in certain limit cases, they turn out to be equivalent. And I think there are a lot more of theorems or formal results in this field that one could use to further specify the relation between the two ways of thinking about the implicit structure. I just gave you these two limit cases, but I think this is worth looking into in future work. Okay, I think that's it. I should stop here and leave out the equivalent stuff.
Any questions, remarks?
Yes.
Maybe one question, but very general. So, are there other sciences apart from mathematics where this duality between language and variance, say, is considered, studied, or linguistics, or sociology, physics?
Thanks. One field where this is discussed extensively is logic, philosophy of logic. So the paper by Engström and Bonnet that I mentioned, this is one paper in a kind of research program on finding a suitable demarcation between logical and non-logical constants. So or put differently, the idea is to characterize logical constants, demarcate them from non-logical ones. And here, going back to Tarski's work, the idea of permutation invariance or some other forms of invariance was suggested as one way to go here. So at least in logic, there is a strikingly similar analogous debate, but not concerning structural properties, but really logical notions or logical operations. And this, as I said, goes back to Tarski. I forgot when this was a posthumously published lecture or talk given by Tarski, I think from 1966, and it was published much later. What are logical notions is the talk given by Tarski, where Tarski says, Tarski refers back to his 1936 paper on logical consequence. So he says, I've given a definition of logical consequence, which is basically the modern model theoretic definition. But what I didn't specify in that 36 paper was which notions we should consider to be logical and which we should consider to be non-logical. So in 36, he left that open, right? He was skeptical as to whether one can actually make a demarcation. And then in 66, he returns to that topic and says, here's a here's a proposal, here's a suggestion how to characterize logical constants or logical notions. And his proposal is to say that those logical notions are, those notions are logical that are invariants under all permutations of the domain considered. So an invariance criterion for logicality. And interestingly, this idea is motivated directly by mathematics. So in that paper, in the 66 talk, Tarski refers to Klein's program, to Felix Klein on geometry, and says that if one generalizes this Kleinian program and looks at the most general group of transformations, namely all permutations of a given domain, those notions or those properties that turn out to be invariant relative to this very general group of transformations, those are the logical ones. So so in Tarski it's motivated by mathematics. And so in that debate, it plays a big role. Yeah, in physics, I'm not sure. I think people work on this, but I haven't read this in detail enough to say anything.
Yes, thank you very much for your talk, but I had a problem all along.
Yes, okay, sorry about that.
No, perhaps it's my deformation with studying legal, but the problem is the question of language. I mean,
yes.
Yeah, because in sometimes I had the impression that you are talking about structure which are in a language, because in other times that you are talking about structure independence of any language.
Yes, yeah.
I mean,
yeah.
when you use the notion of model, I think it's the question of Shankar.
Yeah.
When you use the notion of model, I understand it when it's a model that which is relative to a formal
yes.
language. That means a language that I can completely describe and which I can give roots.
Yes. Yeah. Yeah. Yeah.
But out of that, the notion of model is for me opaque. I don't understand exactly.
Yeah.
It could be instantiation. Yeah, okay, that's the idea that you have an algebra and that you have a different domain, but it's not the same thing as the idea of model as the class. When you are talking of the classable models, for example.
Yes. Yeah. Yeah.
And the same thing appears here because, okay, if we are talking of definability as probability, it's a notion which is related to language.
Sure.
What is definable inside the language, what is formally provable is inside the language.
Yes.
Then the question is there any notion of probability and definability independent from language? This is the question of Gödel.
Yeah.
That means what is definability independent of any language? He said definability of any language means comprehensible by our
yes.
mind.
Yes. Yeah.
And probability independent from language means the set of all operations that any human being can understand. So it's very vague, but it's something that it's something which enters when what is the interest of speaking of structure instead of speaking in the in set theoretical or the other? Because exactly structure is something that doesn't need formal language. So there is something which is intuitive, which is geometrical, topological. So you can have other kind of so I don't know if it's very clear what that.
No, thanks.
This was my.
No, I think that's is there a point on this?
Another question.
Okay. No, I think that's a very good kind of comment or worry that you had actually. I mean, what I'm trying to do here is cashing out this notion of implicit structure. And as I said, I assume that there is some form of primitive structure. So the objects that I consider, those are structured objects, right? So those are number systems or graphs or these incident structures, right? So they come with, that's the point, they come with some internal structure, right? These are structured objects, right? And now I think one could think of them as just set theoretically without corresponding formal language of that of the signature required. So I think, for instance, with the example of incident structures, you can just say that they are sets that have these properties. But of course, in our modern model theoretic understanding, these things, the incident structures, they come with a language of a certain signature, right? So they come with a, say, first order language with a signature of a set of non-logical constants that have a unary predicate for points, a unary predicate for lines, and a binary relation symbol, a binary predicate for incidents, right? And in that language, the axioms of these primitive objects are formulated if you formalize it, right? So the axioms of affine geometry are stated if you formalize them in such a first order language with these three non-logical constants, right? And I take that as a starting point. So I have no worry with this. I think the question is then, if you try to cash out this notion of implicit structure, there are two ways to do. And the one way, the invariance theoretic approach, does not rely in any form on this formal language that you usually take as assumed, right? Or take as given, right? Whereas the definability approach obviously strongly depends on that language, right? It depends on whether there is a formula in that language, so the language of finite geometry, of incident structures. If there is a formula in that language of incident structures that defines the local extension of that property or relation in a given structure. I think that's the point that I want to make. If you just think about structurality or structural properties in terms of invariance along the invariance approach, language doesn't enter the picture. It only enters the picture at the very beginning when you set up what objects you talk about, right? When you give an axiomatic specification of the type of systems you talk about. But then it's kind of language independent, right? And that's conceptually speaking, that's a central difference between the two approaches.
That's where I have a real difficulty. I mean,
yes.
I set it up in terms of language, and then it's language dependent. All it means is just dependent upon the language to begin with, right?
Sorry, please.
Invariance is also language. You set up the axioms.
Right, yeah.
Language, but they depend upon that language. It's not that you're language independent from that point on. You just depend upon that language itself. I suppose part of what I'm trying to, I think, you may partly ask my question is because it's not clear to me what the relationship is between the axioms of the system and this notion of implicit structure itself. Because I was thinking, for example, of the two axiomatic affine plane decay. If you just look at the definitions, I try to just translate them away from set theory to kind of everyday language. The funnel plane basically seems to specify a set of points and lines so that you can't have parallel lines in it. That's the only sections, right? The affine plane basically sets up a set in which every line is defined by two endpoints, that you can have both intersections and there have to be parallel lines in it. And there has to be a plane. So you have 3 points, you don't reduce it down. So that's if you want that plane, all geometries of that type are affines, all geometries that exclude parallel lines are the other. Once you've done that, you've already set up the structure.
Yes, yes, yeah.
So what are we talking there about? Second order structures as being right structures? I mean, the axioms already encode in the terms of their definitions in that language of what a point is, what a line is. The objects encode them as well, because you can't have these relationships without certain objects. And then you've already defined by those axioms that have a certain space. I can imagine then a visual set of planes that will correspond to affines that can visualize and others. But it's already done in that language itself.
Yeah.
So that where is implicit structure? Is it on the axioms? Is it on the, or is it only second order things to derive on that? So I'm just trying to get a sense of. Am I being clear?
Yeah, no, thanks. That's a very good point. So as I tried to emphasize, I fully accept your description of how you set up what I call the primitive structure. So set up the objects in the first place, and you need, if you do this in a formalized way, then you need the formal language to state the axioms. And I mean, what do the axioms do? What do you do with the implicit definition by axioms? Well, basically you state certain primitive structural facts that any object has to satisfy in order to count as an affine plane, for instance, right? So basically the axioms expressed in that language specify conditions or basic structural facts that any system has to satisfy in order to count as such an object. So I think that's really unproblematic. So I take that for granted. The question is then, how do you investigate the implicit structure of these objects? So the structural information contained in these objects that is clearly not explicitly stated in the axioms, for instance, right? It's not explicitly stated. So to paraphrase this Winnie quote, how do you make the implicit structural features explicit, right? Maybe that's and the two explications that I offered, or ways to make this precise, can be seen as two ways to make the implicit structure explicit. And the important point, I think that relates to your worry, the important point is the one approach in terms of invariance that doesn't make use the language. You used it at the beginning to specify what the objects are, but then interestingly, you don't need the language to specify, to make the implicit structure explicit, unlike in the other case where you really have to make use of the language that you started with to carve out those features that you want to characterize as structural, in the sense that these features or relations preserve the implicit structure that you started with, right? That's the idea, or nothing is added to the implicit structure.
Yeah, I'm sorry, I had a question. I need some concrete things.
Yes, sure.
I don't think I really get it was quite abstract for me, sorry. But let's think, for instance, for to a cellular automaton.
Sorry.
Cellular automaton.
Okay.
There are very, very, very simple rules.
Mm-hmm.
So I would say that definability, I'm not sure I understand what it is, but the way to define the basic things is really, really elementary. And we know it can evolve in a totally crazy complex, as complex as we want.
Mm-hmm.
So I would say that you can, I mean, there is no limit to complexity, of course. So I would say that you can have invariant as unpredictable as you want, if you let the cellular automaton evolve. So is it is this related to what we're talking about, or between this elementary definability and this impossibility to even talk about invariance you could construct in this theory, if you let it evolve? Or am I totally?
No, I'm not sure if I fully understand your point, but I think let me try to say something. I don't know if it kind of connects with what you're saying. So maybe let me actually go back to this to make it very concrete, right? So these are the starting points. So objects like this one, okay? I mean, this is very nicely, you can visualize it, you immediately see it's a finite thing. you can see that you have some parallel lines here, the finite number of points, right? So, and these things, as you mentioned also, these are specified axiomatically. So you give you state these axioms, and since this object here, this diagram here, has the properties specified in these 3 axioms that I stated, it counts as an affine plane, okay? And it's a very simple, intuitive object. But interestingly, it has a lot of quite complicated implicit structure. There's a lot of quite complicated implicit or structural features in it that are implicit. They're not specified in the axioms. And now the question is, well, how do you cache those out, or how do you make those explicit? And the 2 options that I outlined are tools used by mathematicians to do so, to make the implicit structure or structural feature of this object or objects of this kind explicit. And I mean, I'm repeating myself, but looking at the invariance conditions is one standard way of caching this out, and specifying properties in terms of definability in the language that comes with this object is one way. I mean, if I see this object, so this is language independent in a way, but I mean, if I see this, I have my first order language of incidence structures in mind. So I have no worry about this. I take this to be a thing that's described in a first order language with 3 non-logical constants. So I fully take that thing. But if you look at the automorphisms of that thing and the stuff that's preserved by them, you don't need that language. Oh, sorry, there's one in the back, but I don't know who was first.
I have a question about the definition of what is structuralism in mathematics.
Oh, yes, yeah.
In the first part of your talk,
I should go back to that.
Yeah,
this one.
Yeah. You were talking like if a structuralist in mathematics is focusing on the relation between the objects and not focusing on the essence of what is a mathematical object. And I was thinking about the fact maybe there is no such a thing as an essential property of mathematical object. And so is it interesting for you or important to make the distinction between a strong conception of structuralism saying that there is absolutely no something like essential property of objects, and maybe a weak conception of structuralism where you say, well, maybe there are essential property of objects that mathematicians are not interested by this kind of things, and maybe this distinction could be important when you make the distinction between two ways of speaking about mathematical objects by automorphism, by transformation and invariance, or by axiomatic definition. Because when you define an object by an axiomatic definition, like in the program of Hilbert, you make as if there was not other properties than structural one. But if you define an object through representation, for example, if you speak about a vector, not with the axiomatic of a vector space, but starting with a coordinates definition of an object and then making automorphism, then you have properties that are not. So this difference between saying that there is no non-structural properties for mathematical objects, or there are, but we don't focus on this.
Yeah.
It's clear.
Yeah, it's clear. It's clear. It's clear. Thanks a lot. I think that's a very good point. I think or question.
I could
Sure.
take that same point in another direction. What I was thinking of when I said that was thinking about Leibniz, for whom every mathematical truth is analytical, and therefore everything must be, which is tautologies, and therefore everything must be in the object in some form or the other. But that means every relationship that object has is also going to be in the objects across time and space and everything else. And so that's a kind of
it's related to
in the object itself to begin with, all relationships. I'm not sure how one actually makes the distinction between what's essential to the object and what's the relationship outside it.
Yeah, thanks for that. Yeah, I think that's directly related. I mean, how should I? What's a good response to that? Yeah, I should say this. In the modern analytic literature on structuralism, so Shapiro, Linnebaugh, Hellman, and these people, I think you have both ideas, right? So there are defenders of a more robust realist account of structuralism, and for many of these, or several of these authors, so I'm thinking of Shapiro in particular, one claim that you find in the literature is that really structure is all there is, right? So there are no intrinsic properties. Objects are objects in a mathematical system, numbers in a number system are these abstract positions, and they have no non-structural features. They are completely characterized by their structural features, so by their relations, and that's it. They can be instantiated by concrete stuff, but the numbers in number system, so the number 2 in the natural number system is just a position or placeholder, and as such has only structural properties. And then related to that, to your question, some people in this debate then also said, okay, when should we identify two objects understood as placeholders? And when then Leibniz comes in, so there's a principle of structural indiscernibility, well, the idea is to say, well, two positions are in fact identical if they have the same structural properties, right? So that's the more robust or stronger claim, which you, I think, referred to. And then there's a weaker one, and actually I like that one much better, actually. That's to say, well, you have these objects that you investigate. These are structured objects, so just think of the incident structures. I mean, these are the basic objects that we consider, and there are elements in there, points, lines, numbers in number systems, and these can have all kinds of properties, right? I mean, what are the typical examples? The number, I don't know, 7 being your favorite number, or the property of being an abstract thing or so, right? So clearly non-structural properties, but the claim would be, the structuralist claim would be, well, the interesting ones, the ones that mathematicians are interested in, are the structural properties, regardless of what other qualities or features they have. I think that's a much more defensible or interesting claim. And I mean, I think this first working definitions, that's how I would understand structuralism. That's my, as I said, deflationist account. Yeah, that's how I like to view it. And then to this other question, how that affects the two ways of thinking about implicit structure. Well, you can be a deflationist like this, and then still you have both options, right? So the two approaches, the invariance and the definability approach, you can free to choose either one or compare them. They're both compatible with this deflationist account.
Maybe a last question? Yes?
I wanted to ask this before the discussion about like language. What are we
Yes, yes, yes.
I think maybe it makes it more like not answerable. I don't know, but about the difference between invariance and definability. Like you were saying that it's not equivalent, but that in some cases you still have the invariance implies definability in some cases.
Yeah, or yes, yeah, invariance implies definability. Yeah.
And I was wondering if there were cases where, like, it was formally you could say that this relation, this property is invariant, but not definable.
Oh yes. Oh, so or examples that turn out to be invariant but not definable. Yes. In this, in this paper that I mentioned with Johannes Korbmacher, we discussed a number of examples. I mean, there are what should I say here? The notion of implicit structure or structural properties in the second approach, the definability approach, obviously depends crucially on the logical strength of the background language that you use, right? That's I think Michael Resnick in his work on structuralism has called this the structural relativity, right? Really depending on whether you work with a first order language or a second order higher order language, different properties would turn out to be definable, right? And sorry, as I said, in the limit case where you have a very rich artificial, one could say, account of language in infinitary language, they turn out to be equivalent again. But I mean, also in looking at the practice, mathematical practice, there are clearly properties that are invariant, but they are not definable in a first order setting. I forgot which examples we had in mind, but if you... Sorry?
In what? In first order?
That are not, so there are examples that are not first order definable, properties that are not first order definable, but they turn out to be definable if you add to your language relation variables and quantifiers binding them. So I think one example that we discussed is I forgot, but some graph theoretic example where you have to quantify over sets of knots.
But
right?
does that mean that for any invariant, you can always specify a language of sufficient robustness?
Right. So then you can tweak of course the logical strength, and then properties that are invariant but not first order definable become definable, right? But I think that generally, unless you reach this limit case of